Greetings. This is the midterm for week 11, which will be in the Pollock Testing Center. Same as last time, all tests, closed notes, closed book. You can take a calculator and a pencil along with you, and there should be scratch paper provided. The equation sheet will be at the bottom of the exam scripts, just like it was previously, and it will be the material that we'll talk about today, just as a screen capture. All three of the tests are available in Pollock, or are in Pollock only, and so you'll get an email, I guess, a week ahead to schedule for a particular time during the day, and it'll be exactly the same format as the practical exams. The material is from week 4, excluding the first session, which was really acceleration of static fluids. So it's really Bernoulli, fluid dynamics. It's talking about conservation of mass, which are control volumes and changing control volumes, and conservation of linear momentum and rotational momentum, although I think on this test there is no rotational momentum question. The topics for the 3 questions in the scheduled exam. The first one is a question on free jets, which you use Bernoulli to get the expressions. The second one is Bernoulli and using conservation of mass. And the third one is using Bernoulli and also conservation of linear momentum to solve for forces on structures, as we've done in the past, on moving structures in this particular case. So the material is Bernoulli onwards. You know Bernoulli's relationship. You write it from upstream to downstream for these 6 parameters. So far, it doesn't matter that it has to be upstream and downstream, but it's easy just to use that convention. If you have 5 knowns and only 1 unknown, you can solve it directly. If you only have 4 knowns, then you have to constrain it somehow, and usually you constrain it by writing a simple conservation of mass within the stream tube, where you can write mass rate in equals mass rate out and link the magnitudes of the velocities to each other through those geometric cross-sectional areas, and therefore constrain these to be just a single parameter instead of 2 parameters. We talked about Bernoulli defined in terms of a graphical description. So far we haven't talked about pump heads or head losses, so everything we have is that everything is limited by a horizontal energy grade line. And so we can think about flow along a pipe, if you like, that's from an upstream elevation to a downstream elevation. And physically what the 3 components of Bernoulli represent are an elevation of the location of the pipe, the pressure that location feels, and a velocity head, which is represented by the velocity along here. If the pipe cross-sectional area is constant, then these 2 velocity heads have to be equivalent to each other, and therefore we can scale the magnitudes of the pressure from that. If we think about a pipe that goes up some elevation in this particular case, then we can use that to be able to calculate the magnitudes of the pressures and the elevations in that pipe, just by realizing that within that pipe, I guess it goes down to here, right? Within that pipe, then changing color, this would be the elevation of that point. This would be the pressure head of that point. If this is exiting at atmospheric. If it's not exiting at atmospheric, then I guess we would go down to this point here. And then that would allow this component here to be the velocity squared term. So elevation, pressure, and velocity head. This has to be sub magnitude of pressure. So this magnitude is lower than the magnitude here. So we need to be able to accommodate that. We talked about moving coordinate systems. That's pretty straightforward in that if we look at squirting water out of a boat at some velocity w, and the boat is moving at a control surface volume of VCS, then the sum of those 2 is what a static observer sees. And so the sum of those 2 vectors gives you the vector for static observer, the velocity of the control surface, and the velocity of water coming out of the boat relative to someone standing physically here on the boat. We can use Bernoulli to describe the behavior of a variety of different flow structures, one of which we talked about was free jets. If we define the pressure and velocity at the surface of a large tank, which is zero velocity on the surface, we can calculate the velocity if we know the components of the behavior at other locations. Here, if the fluid is coming into the air, the pressure is at atmospheric, so the gauge pressure is zero. So writing Bernoulli between this upper and lower points allows us to define the velocity of the free jet as being equal to square root 2gh. 2gh is just the vertical elevation change between these two locations. If we want to figure it out at this particular location here, then the value of the head is just this green h value. And of course, Bernoulli doesn't care about the direction. It's just a streamline velocity. So the free jet velocity horizontally in this direction would be exactly the same as the vertical streamline velocity in this case for a tank with a hole in the base of it. If we have the free jets coming out, we know it's exactly the same behavior as if we were dropping a weight, and so it will tend to fall under gravity, as it does here. We did a simple calculation in class to show that indeed the convective acceleration at this point is equal to the acceleration due to gravity. But if we know those behaviors, that it will fall due to gravity at this point and it will keep on moving at velocity v exit horizontally, we can use those to calculate exactly the arc of this behavior. We can use a statics equation that gives us a distance traveled as a function of an initial velocity and an acceleration to be able to look at vertical or horizontal behaviors. And we can differentiate this expression to get a velocity as a function of the change in elevation or location z as a function of time, which is just the derivative of this equation. So nothing that you haven't seen in your statics and dynamics classes. There is no manometer equation, so you don't have to worry about that. Conservation of mass, the simplest exposition of this is this expression here. But we can do much more complicated things with it by linking a control volume, which no longer is a streamline. It's kind of a streamline in this case, that has a control surface applied to it, and that has an upstream and downstream. We can write the conservation of mass equation as a change in the product of mass and density and volume, as in this term here. If we differentiate by parts, we get a volume multiplied by a rate of change in density plus a density times a rate of change in volume. We've explained these components, that this represents a tire which is being inflated, where the volume of the tire remains constant, but the density of the gas that's going into it has to change. We've talked about this term being filling a bucket, where the density of the fluid that's going into it, say water, remains constant with time, but the volume changes as it fills up. And so these are the components of accumulation, and those have to be balanced with mass rate in equals mass rate out. And so we do that in terms of a sign convention. The sign convention is that if density increases with time, or volume increases with time in these expressions, those are positive. And a mass rate out of our control volume is also positive. So the sign convention for the accumulation terms is this. The sign convention for the mass rate into the system, which we can just write as the density times the cross-sectional area of flow times the relative velocity across that surface. And the sign convention, because this really is a dot product, the sign convention is that the dot product of the outward normal and the velocity, they're both aligned to each other. So that's a positive mass rate out. And this is a mass rate, a volume rate in, and a normal to the boundary velocity, which is opposite it. The dot product is negative. So this velocity would be a negative velocity, corresponding to a negative mass rate, which is a mass rate into the volume. So we can use that to define conservation of mass. If we use conservation of linear momentum, which really is just what we've seen before, F equals ma, then we can write out this expression here. This is just mass times acceleration on the right-hand side. This is sum of forces. Again, we write it on a control volume, which has a control surface that goes around it and a control volume contained inside it. We can write this conservation of linear momentum equation in terms of forces, sums of forces being equal to the products of velocities in Cartesian coordinates and mass rates of flow defined as in or out, as we defined here. And these are actually three equations. And those three equations are actually in the x and y and z directions for different forces. And we can choose to take any one of those and resolve for those. But we need to get our sign conventions right. So if we write it as a single component, in this case in the x direction, then this is the force in the x direction, which is positive in the positive x direction. So these are in the Cartesian coordinates. This velocity is also a Cartesian coordinate, positive in the positive x direction. And the mass rate of flow conforms to the mass rate in, which is negative, and mass rate out, which is positive in this. And so if you look at the sign convention for these, the sign convention that's applied on the mass rate, if it's out of the system as a velocity, well, actually, not here, velocity v2. Velocity v2 is positive because it's out of the system. It's going across this boundary. And volume mass rate number 1 is across this boundary here. It's going into the system, so it's negative. So that's the same, exactly the same as it would be for this system. It's just that we've drawn this going out through the top of the control volume. The components that represent the velocities in this term have to be in terms of the Cartesian coordinates. This velocity is in the positive z direction, so it would be positive. This velocity is in the positive x direction, so it would be positive. And so when you do the accounting for all the individual terms with the proper sign convention, you need to account for these proper sign conventions, which we've always kind of bracketed ahead of these terms to be able to make sure that you're adding things in the right direction. If we want to define behaviors in terms of a moving coordinate system, this is the static velocity. And so we can always write that static velocity in terms of this component here. So the static velocity is always the sum of the velocity of the control volume plus the relative velocity of the fluid relative to that. So if the hose is squirting at velocity 1 meter a second, is moving to the right at 1 meter a second for the boat, then the sum of these two components is equal to 2 meters per second. And so we can substitute this velocity here with that term. It ends up being this term here, and we can use that to be able to solve the systems of equations, and we've done that. For rotational velocities, we can multiply both sides of this by the radius of rotation. There is no rotational velocity question in this test, so you don't have to worry about that. But you do have to think about this relative velocity term in the equation. We talked about a couple of different solutions. We talked about solutions which are static and those which are steady. The static solution we talked about was the jet lev, where it's just being elevated by a jet of water which is being squirted down. It's not moving in any direction, and so that represents a static control volume, in which case the control surface is moving at velocity VCS equals 0. And we also would have talked about a moving coordinate system where fluid goes into the system and out of the system and has a finite non-zero control surface volume, where this control surface volume no longer is equal to 0. In all of these, if they're steady, and we've only talked about steady problems for these systems, then the mass flow rate, mass rate in equals mass rate out. That's the definition of steady. And if that's indeed the case, you can actually get rid of this term, because as the control surface moves at some velocity VCS, it sweeps out a velocity which is the same on the upstream side as it is on the downstream side. So these velocities actually cancel out from each other. So for a steady problem, this is equal to 0, and therefore you're left with this relationship here, where you've just set this equal to 0, and you're left only with the relative velocity term. And you can calculate the forces that are applied on the system to be able to define the behavior. You can always get the magnitude of this mass rate, flow rate, as being the product of the area, the density of the fluid that's influent or effluent, and its velocity relative to the boundary. And you can always calculate the forces that are applied. If it's a moving control volume, then VCS is not equal to 0, and therefore this term is active, and therefore you need to include this in your relationship for summing these components. And of course, the simple analysis from this is that if that is active, the only time that the force that's acting on this body can be 0 is if these are equal and opposite to each other. And so the maximum velocity that this can travel at is equal, the control surface is equal to the influent velocity of the fluids, which is the kind of short answer to what goes on. The other problem that we talked about was an unsteady problem. So the three examples we talked about were the jet lev, the moving vane, and also the decapitated gas cylinder. And that is an example where we have to account for the fact that it's not steady. If it's not steady, then we can no longer set this value as equal to 0. It's moving at some velocity VCS. The magnitude of this is equal to the area times density times the velocity that's coming out of the system. But we have to be able to accommodate this magnitude of these two. And again, as before, the only time that this can equal 0 when it's released is if these two components exactly balance each other. So we have a control system that is traveling at the effluent velocity of the fluid that's coming out of this decapitated cylinder. Finally, I guess we can talk about power that's generated from these machines. The two end member conditions that we can talk about these systems, say for the vane, is one, if you're holding it static, then the velocity by definition is equal to 0, and the force that you have to apply to hold it in place is a maximum. The converse of that is if you're allowing it to move, if you provide no force to restrain it, then the velocity the vane will move at, the control surface velocity, will be a maximum. And so those two end member conditions kind of define the behavior of a system, either clamped or released. And so the case when you hold it static, then the force that's generated will be a maximum. And the converse of this, if the force is released, then the velocity of the system will be a maximum. And so those two end member behaviors, if you plot it on a graph that gives you the restraining force relative to the velocity of the vane, if it's fully restrained, the velocity of the vane will be equal to 0. So fully restrained is this case. The velocity by definition is equal to 0. If the vane is released, then there'll be no force on the system, which is this, and the velocity of the vane will be a maximum. If we define work as equal to power, which is just the rate of doing work, which is a force multiplied by a velocity, then this force and this velocity of the vane are the two components that go into that. At this particular ordinate here, this force is a maximum, but the velocity is 0. So the product of force times velocity at this point, at this velocity, has to be 0. If you look at this point here, where you've released the vane, and its velocity is a maximum, but the restraining force is 0, then again the product of those is 0. So the power that's recovered from that system is 0. And so at intermediate points, the force here will be equal to half of F max, and maybe the velocity of the control surface is also roughly equal to a half of that, and the product of those will be a finite number. And so it won't necessarily be a maximum in the middle, but it will look something like this. And so to be able to get power out of this system, you have to unclamp it and provide some resistance in terms of a force. And at that magnitude, it will return a finite magnitude of power from the system. And so you can use that to calculate the power in the system. So that is about it. So those are the things that you need. I think if you scroll down here, this will be on your equation sheet, but as I've already mentioned, there is no rotational question on it. But actually, just for laughs, this vane with influent flow here and effluent flow here is exactly the same as the geometry that we're talking about here, except that the motion in this particular case is some kind of rotational motion around a pivot point. And so this, you can see the direct correspondence between rotational momentum and linear momentum. We just use a different coordinate system, but really they're rather the same. And of course you can calculate power in the same way by using the force times the velocity of the control system, which for our rotational system turns out to be a force times a lever arm, which is a torque, multiplied by its rotational velocity in terms of radians per second. But as I mentioned, just so there's no confusion, there is no rotational velocity question in this particular test. Okay? That's it. Good luck on the test. Thanks very much.